Hi, my name is Marc and I'm going to talk about our sequence of constraints MPC paper at IROS. Let me motivate the work stating there's very strong arguments for task and motion planning. Here's some early work by Mordach, which generates really fascinating complex behavior. Here's some work of our own, which is based on what we call logic geometric programming. Here's also an application of that LGP work on architecture assembly. And there's many other strong labs that proposed very strong task and motion planning algorithms and generate very complex behaviors. The question is, how can we bring such complex behaviors on real systems? That is, what is a framework for robust reactive execution of such plans? Let me mention briefly what I mean by robust. So I find this work by Boston Dynamics really inspiring, where this little system, Spot Mini, is going through like a sequence of behaviors being interfered with quite heavily and is very robustly executing this. Here's also very strong work from Freiburg, which is quite similar in terms of the robustness. In terms of related work, there is more work which tries to think of the output as time planning as trajectories and tries to follow these trajectories, or which a priori assumes that actions in task and motion planning are related to control primitives. Our work takes a different approach. So we assume that the output of task and motion planning is a sequence of constraints, waypoint and running constraints. So waypoint constraints could state that in the final time slice, a red object would have to be at a target location. Running constraints could mean that in a phase before that, a finger needs to touch that red object and push it in a direction towards the target location. And if you want to robustly execute such kind of sequences of constraints, we want to be robust to change of the situation at any point in time. So for instance, if the target location changes, then this should propagate back all the way to how the finger is right now approaching the object, so that it's approaching it from the right side to push it then later in the right direction. Also, we want to see a behavior where if some of the running constraints are being missed during execution, then the system should try to reinitiate that kind of phase. So we follow an MPC approach, but we actually include in every MPC cycle optimizing our waypoints, timing, and the receding horizon path. So the waypoints represent the configuration of the full world, also in the far future, which means that by optimizing and adapting waypoints in every MPC cycle, we kind of react to any changes in constraints that refer also to very far future situations. Then a core insight of this work is that we also have to optimize the timing of these waypoints, because the timing of waypoints relates to gains and aggressiveness of the controller, and it's really essential actually for our system. And then we also have the more standard receding horizon problem, which tries to find a shorter horizon path which fulfills all running constraints, including collision avoidance and everything. So here are our equations for these subproblems. This is the original full problem. If we could solve that in every MPC cycle, then we would have kind of an ideal controller, but that's too complex. And we decompose this approximately in subproblems like optimizing waypoints coarsely, optimizing their timing, where we have a mixture of time optimality and control costs, which leads to a very nice sum of squares problem, which is efficient to solve. That's core contribution of the paper. And then the more standard receding horizon trajectory optimization problem. There is more technical details in the paper which discuss to what degree these are approximations, some kind of sanity check theory that the two MPC cycles are consistent, some kind of comparison of the gains that are implicit in timing optimization to linear regulators, and also a discussion of the fact that you cannot actually, a noisy system can never exactly transition through constraints and how to deal with that. So let me show some demonstration of the controller. So what you see here is about almost 2 minutes of execution of the controller on a single control chain. There is no further outer looping or so. This is just without a cut, a single execution of a control chain. The goal here is for the red object to touch the green one, and it needs to be pushed to be touched. But very often the running constraints of pushes are being missed because the red object moves to the side, and then the controller automatically reinitiates that phase, and this is why you see this looping behavior. You saw here a really interesting behavior where I'm changing the target location, and the system reacts immediately by changing the approach direction 3 phases earlier in that chain, which is exactly the kind of behavior we want to see. So we have more demonstrations on pick-and-play scenarios where, I'm stealing the block and things like that. Here's pseudocode for a single MPC cycle. So we cycle it with about 10 Hertz. And some part of that code is about the phase management, which checks whether constraints are being missed and then backtracks. And the core is in red here, which is this solving the waypoints, the timing, and the path in every MPC cycle. Let me conclude with limitations. We assume perfect knowledge of the position of objects. We used OptiTrack. Let me point to actually related work in our lab that tries to formulate constraints based on images only. And if we could combine that, then all the constraints that we need for this controller actually are image-based. And also, the current work only is about controlling a single sequence of constraints. We have like a related work here at IROS, which is on the next higher level, which is actually about controlling plan switching. I want to conclude with a bit more conceptual point. A standard way to organize behavior is to think about motion primitives and motor skills. Actually, in this work, the control framework is very much based on constraints. So the core abstraction are actually constraints, not motion or control primitives. And the higher level decisions, also in time planning, they relate to imposing constraints on the control level and not choosing like motion primitives. And the complexity of behavior actually comes from the compositionality of constraints and not really from the compositionality of motor primitives, something like that. And this constraint-based view on abstractions, manipulation, and control is not really novel. There is some prior work, as this one, for example, and it's really the foundation of our approach. These are the authors. Thanks for your attention. You find more videos and code on this page here. Thank you.